This is our second video about components on a plane, components of a force on a plane, where we're going to look at what happens when an object is on an inclined plane rather than being on a flat surface. And the first question that we're asked is, will the box remain at rest or slide down the plane if the frictional force acting on the box is 15 newtons? So the first thing to think about is, well, there's a frictional force pulling on this box. It goes in this direction. That's equal to 15 newtons. And friction's a force that opposes a motion. So we expect this to try to slide down here. If the frictional force is strong enough, it should stay in place. So what we have to do is figure out what is the force that's actually making this go down. And going back from the prior video, we know that the main force acting on this is gravity, which is simply just going to be the weight, or mg. So in this case, the weight, or mg, is going to equal 10 kilograms times 9.8 meters per second squared. Oops, second squared, a little messy, but the idea is you end up with 98 newtons of force. So now if I go back here and kind of change this, this is really 98 newtons. Drive it a little bit farther outside, give myself some room. 98 newtons. All right. So we know that part of this force is pushing into the plane, but part of it is actually going down the plane. So what we want to do is kind of break that up into its two parts. So we have part of that going this way, we call that our perpendicular force, and we have part of it going this way, we would call that our parallel force. And what we're looking for is the parallel component of this force right here. So remembering back to the prior video again, we know that this angle, based on the geometry from that one, is 20 degrees. So what we need to do is find this parallel force that's pushing this down, created by gravity. And if it's greater than this 15 newtons, we know it's going to slide down. To do that, we are going to use our sine function. Sine theta is equal to the opposite side over the hypotenuse. So we fill in our numbers, our known values. Sine of 20 degrees is equal to the opposite, F parallel. We are looking for that, divided by the 98 newtons that gravity provides for the weight, and the parallel force is going to equal 33.5 newtons. So to answer this first is this will not stay at rest. It will basically be going down the plane because there's only 15 newtons going back, and if I kind of add this vector in here, there's 33.5 newtons pulling it forward. So we know there's a lot more going down. So the question now is, what is the net force? So if we just simply find the net force, we know that's when you take the forces one way minus the other. So we have 33.5, as long as we're going in opposite directions, obviously, minus 15 newtons, and we end up with a net force that is equal to 18.5 newtons. Okay, so we know that's how much force is pulling that down the actual plane. So kind of shifting colors because we're shifting gears a little bit here. We want now go to our second question. If not, find the acceleration and the speed at the bottom of the plane. Acceleration goes back to Newton's second law, F equals ma. And we know then that a is just going to equal F over m. And again, what's making it move in this direction along this plane? It's 18.5 newtons divided by 10 kilograms, which gives me an acceleration of 1.85 meters per second squared. So we found one part for the second question. And the next thing is, what is the speed going at the bottom? Now we're assuming that this frictional force stays relatively constant. It's always going to be the same, and then so does this force pulling it forward. So we can use as our Suvat equations, and in this case, because there's no time involved, the equation we're going to use is this one. V squared is equal to u squared, u squared plus 2 times a times d. Now u is equal to 0. There's no starting speed, so what we really end up with is just 0 squared plus 2 times our acceleration, 1.85 meters per second squared, times the distance, 0.5 meters. Then v squared equals 1.85 as it turns out, meters per second squared. 0.5 times 2 is really just 1, so we end up with the same thing. And it's meters squared per second squared. We have to keep this meters times meters in there. The square root of that is 1.36. meters per second. So that will be the speed at the bottom of the incline when it reaches this point down here. This concludes the next video in our components of the force on a plane.